Good morning.
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 Welcome to Aruba's Proof of Concept Lab. My name is Paul Curto, and we're very happy to host you guys here today. I've been part of the technical marketing team here for a number of years, and this facility that you're sitting in is actually owned and managed, functionally at least, by Aruba's technical marketing team. So as you can see, there's a lot of toys in the room, and we're going to have a lot of fun today, hopefully, walking you through a series of demonstrations, live demonstrations of Aruba technology. I want it to be very interactive, and hopefully we'll have a pretty good time. We're going to get started today with a discussion around setting the context for BYOD. This is clearly a high-performance testbed that you're sitting in now. So as we walk through some of the demos that offer some of the proof points behind some of the concepts that we're talking about, for example, multicast video at scale, we have back here a demonstration of over 40 laptops that are going to be running high-definition video. A mix of BYOD devices we're going to show you that are on the table here. Each of these pods represents a user who's bringing a set of devices with them. It could be a tablet, a smartphone, and an enterprise-class laptop. What is the impact of that kind of mix at scale in a high-density environment? And then we're going to talk a bit about some of the types of applications in a BYOD context. So this could be applications that the user is bringing with them to work. That could be personal applications or enterprise applications, and also cloud-based applications. How do we provide some visibility into those, and how do we prioritize those and give them quality of service if we want to? And then lastly, we're going to close this session with a discussion around the large public venue, which is taking high density to another level of scale. And so we'll go through that, hopefully at a fairly quick pace for the slides, so we can get into the demonstrations. So to start off, applications driving networks. We know that we have different devices. This is more of the traditional type of slide where you see desktop PCs, fewer applications per device, VoIP phones, which are really single-purpose devices. They have a single application purpose. Laptops, obviously, and then other devices like printers and things that have perhaps a Wi-Fi interface. Of course, BYOD brings us new types of devices, the tablets and the smartphones, where you have many applications per device. Some of the issues here are now we have a mix of personal and corporate applications, and each one has a different security and quality of service context. So in terms of cloud, private cloud and public cloud, the private cloud is really the IT control domain, where we have a little more OpEx intensive, so weeks to roll out, local maintenance, you have to touch the user's devices, you have a standard set of applications. Then the uncontrolled applications are really the public cloud. This is where the end user is in control of what applications are running on their device. This is all running on the same Wi-Fi network on the same device. So you have a mix of these types of applications converging. Let's talk a bit about some of the characteristics for enterprise class laptops. It could be 2x2, 3x3 MIMO, so you're getting up to 450 megabits per second. You have dual radio, primarily Wi-Fi. They're typically going to be fast roaming, a better roaming performance over the wireless network, primarily used for data, and the standby is full standby. When you start to add tablets and smartphones, they have similar kinds of characteristics. The tablet is more of a one-by-one MIMO as well as the smartphone. Typically the smartphones are in 2.4. We just heard the Apple announcement, it's now dual radio. So you're going to see this mix shifting over time, probably more in preference of dual radio designs. As we know, the 5 gigahertz has more spectrum, is going to be a better performing system. The roaming behavior of these devices tends to be more sticky, although we've seen a lot of differences in performance as we upgrade, iOS version or driver version, those types of things. And the tablets tend to be more multimedia heavy, and probably the smartphones are a mix of multimedia and data. And the standby is hot standby for both. Then we have the single purpose wireless devices, the Wii or the printers and the Apple TVs. We're actually going to show you some demos later of Apple TV and some of the Air Group features that we have. These are more multimedia heavy. Multicast DNS, of course, plays a key role. And they're primarily static. So in terms of the types of mobile applications we have, there's multimedia heavy, which are latency sensitive. We have Microsoft Link. We've shown off quite a lot here. We have built-in ALGs for all of these in terms of the Link, virtual desktop, as well as FaceTime. So we're able to, first of all, classify the application with some kind of a heuristic or deep packet inspection type of algorithm. Once we are able to identify that using those methods, we're able to give it priority. The other types of apps are going to be primarily data bandwidth hungry applications, and that's also something we'll demonstrate today. Box.net, for example, which is, in the case of Aruba, one of our corporate standards for where we host a lot of our content. So we're going to be interacting with that application quite a bit. Once we're able to identify that it's a box application, we're able to provide, again, priority and give that preference over the air. So what are some of the best practices? Some of these are going to be pretty obvious, some a bit of a review, but in terms of allowing all device types onto the network, this is really part of the BYOD discussion. In order to do that, we need to be aware of the device type. As you're all probably aware, we have a built-in DHCP fingerprinting in the controller. We have the ClearPass system. We're going to talk a lot about ClearPass later on in another session. But getting a mix of profile information to determine with a pretty strong degree of certitude that that is this device type. And then, of course, we know the user. We have all the AAA infrastructure. We have the integration with the controller. So we're able to provide role-based access control. But the combination of the user and the device information derives another type of role for us that we're able to do things like onboard a device. And then needing to maximize airtime. This is really a lot of the ARM features that we've added, and we'll talk about some of these features and show you how that works. The need to clear the air of unnecessary traffic. So a good example of this would be taking multicast traffic, converting it to unicast, doing things like air group, which takes MDNS and makes it more unicast directed, and really redirecting a lot of that traffic or intelligently filtering the traffic to make the air less chatty, providing more airtime for the applications we care about. And then lastly, delivering quality of service for the applications that we want to. And that's going to be something we'll show you as well. In terms of video scale, we really have a couple of use cases here. The first one talks about taking, really it's this density test here, taking a bunch of enterprise class laptops, maximum performance test, how many video streams can we get? So this example has 20 laptops in 5 gigahertz and 10 laptops in 2.4. This was done by our QA team where we had 6 megabit per second plus video. We're going to show you a bit of a different test in a few minutes on a single radio where we're able to even increase the density a little bit. In terms of iPads, we've seen numbers on the order of about 23 1 megabit per second streams where we're able to get good quality. And then we did a test where we showed a large file download and saw how much battery drain is there when you have your iPad far away from the AP and you download a large file. So we're actually seeing about a 7% drain on the iPad in that test. Not all iPads are created equal. So we've seen this in all of our testing where you start off with an iPad 1, you're probably getting about 26 meg in the upstream and 36 down. If you get up to the iPad 3, this is really where the performance has been enhanced and we're now able to get roughly 46 megabit per second in both directions. So it does matter what version you have, obviously the iOS version as well. These are all, of course, 1x1:1 MIMO. They all have 20 megahertz channels. And it is hard to sustain the 65 meg link with the iPad 1 and iPad 2.
So have this been tested while plugged into the power or plugged out?
I think both ways. Team, correct me if I'm wrong. Do we see any difference in performance plugged in versus not plugged in for the iPad? Any thoughts? iPad testing? Do we plug in typically or unplug? Typically we run without power?
We run it with power plugged in.
Yeah,
Power
because
plugged
there's quite a bit of a difference between the performance plugged in and plugged out.
Mm-hmm.
Most users are going to use it unplugged.
Yeah.
Good points. Good points. So we'll provide the updated version with unplugged for you. That's a good action item. This is our standard slide showing role-based access. We don't need to apply policies to VLANs or ports. We apply them to roles, and we typically have minimal number of SSIDs in an Aruba system, typically a corporate or guest being separated. The types of policies we can apply, which are defined in a central location, are things like bandwidth contracts, blacklisting, time of day restrictions, redirecting to different security services. We'll talk a lot more about this in the context of the network services discussion that Carlos will be leading. And then you guys have seen probably and heard of a lot of these buzzwords, if you will: spectrum load balancing, band steering, airtime fairness, spectrum analysis. These are all part of the maximizing airtime discussion. And we'll show you a demonstration later of spectrum analysis. Really, this test bed here is a good demonstration of ARM features, and we'll show you how we're utilizing all these features together to provide the best-in-class wireless performance for density of clients. Just a brief review, band steering is basically the ability to separate out clients over the bands. Spectrum load balancing is a way to separate clients across channels where you have multiple APs in an RF neighborhood. We care about not necessarily AP load balancing, but spectrum load balancing or channel load balancing. And airtime fairness takes the clients on that particular radio, balances out or partitions out the airtime, independent of the client's PHY, independent of the client's data rate. We really want each client to have a fair shot at sending traffic and receiving traffic. So think of it as a meter for each of the clients connected to a particular radio. So combining these together, we think you get the best performance because you've allocated the clients and distributed them most efficiently, and you're able to partition out the airtime most effectively. And spectrum analysis, which we'll show you later, also provides some visibility in troubleshooting tools. But really what you want is your network to automatically take what's in the air and make the appropriate decision to optimize for that. Cell size reduction is kind of a newer feature. We'll talk a little bit about it, I think, in Chuck's presentation. But essentially what we're doing is limiting the receive sensitivity of that access point to other adjacent channel and co-channel interference to maximize high-density testing environments.
How do you do that?
So what we're effectively doing is getting into the radio level and adjusting the receive sensitivity based on typically a number of different factors, like how far the client is away, what kind of signal level we see from the client, or from adjacent neighbors. And I think to get a level deeper.
It's beyond just the layer 2 design.
It is. It's really down at the radio level. We're able to see what kind of noise. It really says the Wi-Fi decode occurs at some threshold of signal strength. Beyond that, it's noise. And so by adjusting that, we're able to see, let's say in a high-density environment, better simultaneous performance for multiple APs on the same channel. And it also helps to tweak the adjacent channel performance somewhat. We also can partition airtime across different SSIDs. You could have a guest network and say, limit the guest traffic to only 10% or 25% of the airtime. And then dynamic rate adaptation is really about adjusting the rate algorithm to the most optimal performance. Prior to ARM 2.0, we were making decisions that were a little bit different to after 2.0. So effectively, when you see two frames that kind of collide in the air, we were rate adapting down, thinking that the client couldn't decode it. Now we're keeping the rates high and trying it again, because that was a collision and not a client issue. And then in terms of limiting airtime and optimizing airtime, we really have a few different features here. Proxy ARP, this is really something we recommend is enabled all the time, where the ARP response is sent at unicast rates. We have multicast rate optimization for all traffic that is not converted into unicast, so that instead of sending it at the base rate, 6 megabit per second or 1, we send it at a higher rate that's sustainable for the clients connected to that particular radio. And then traffic filtering, there's different types of filtering. So we have multicast filtering, where we do multicast unicast, ARP and MDNS filtering. Air group we're going to show you a little bit later and give you a good example of how we can do that filtering.
How are you determining the multicast rates?
How do you determine the, in terms of multicast rate opt?
Yeah.
So it's really, my understanding is the set of clients that are connected, we know what they're capable of achieving, and we're able to set the minimum, I want to say control channel rate for that set.
So that's the minimum. It cannot go below that. So for example, if a client moves to the edge and it's below the 24 megabit threshold,
Then you'd have to adjust it down to that level.
You have to adjust it down. Can you
Correct.
set it statically so it's just that one client that's get affected? So it's out of the area, so, well, your performance is crap, but everybody else stays okay?
So a couple things. One is multicast obviously is going to go out for all clients, so you can't really adjust it for one client. You do want that client, however, to roam or hand off if they're at the edge of a cell, if there's a better AP nearby.
Yes.
Those are things that we're thinking about. But in general, you're going to have to base it on the lowest common denominator for that cell.
Yeah, but that is a problem because you're talking about devices that are very dynamic in nature.
Yeah.
So and the performance is it's not constant. So it's really heavy.
Yeah.
Okay, you have the static environment here, it's gonna work. But if you have iPads moving around,
More mobile context, I think you're going to have to set it to a lower threshold
Yeah.
that accommodates those clients moving around. And really, you don't want to send much of the traffic out at multicast rates.
Yeah.
You really want to try to convert it if possible. And then just to quickly close here, we have different types of applications. We want to deliver QoS for each type of application. The standard ones are voice, then some slightly non-standard, if you will. The more proprietary ones are MS Link, Apple FaceTime. Again, we have heuristics that identify these applications, provide them quality of service guarantees. And then the cloud apps, such as Box.com or WebEx or other things that are out in the cloud. How do we identify those? How do we get visibility into those and provide some kind of a QoS guarantee? Apple Bonjour, MDNS, we're going to talk a lot about that a little bit later with some live demos, and multicast video, which we'll show you in a minute here as well.
With the QoS part, of course, naturally, you've got to have the QoS feeds being put into the wired side of the network as well. So
That's right.
does that all still feed into the standard wired QoS?
It does, and so what you want to do is, in particular, our controller has DSCP and .1p support and mappings between the wire and the wireless in both directions. So you want to provide that northbound from the controller. You want to provide it between the controller and the access point over the tunnel, and of course at the AP converting out over to the air with WMM. So it has to map end to end. The one thing that's missing though is the application may not support WMM in all
Yeah.
cases.
Yeah, I
And
was
so
wondering
if
that
it
for the-
does, you can
for
turn it
the-
on at the application, native application. If it doesn't, the only thing we really have control over is downstream towards the client. We don't have control over the upstream.
Okay.
And then, of course, all of this is running on the same Wi-Fi network and the same SSID, the same quality of service management infrastructure. And these are some of the basic requirements for the devices we need to onboard. Carlos will talk a lot more and give you an update about the onboarding story, enforcing per-device access policies. In terms of the requirement for applications, we need to detect them, we need to secure them, and ensure bandwidth for the applications we care about.